welcome to the part 2 of analysis of variance session. So, where were we? We were discussing these relationships for the total variation, between variation and error variation. So, let me put it in a tabular form here. So, we have this table. So, this data is taken from the book by N.K. Malhotra. This illustration is taken from here. It is marketing research. The example which I will discuss here is also taken from the same book. So, you can read further if you like to have more information. So, what we have? We have these categories. So, mind it, we had capital N here. Capital N here is sample size, not the population size. So, small n is my group size. Where capital N is divided into C groups, and therefore, C here is the number of categories. So, we have C categories, 1 to C categories here, 1 to N is my group size. We can see the all group sizes are same here, and we will see that the error variation here is between my element y and y1 bar. We can see this here, the error yij minus yj bar. Yj bar is y1 bar, this minus this is error variation. Okay. So, between these implies between y1 bar and y bar, this is my between variation, and for each element for y1, y2, so on up to yn and so on for category 2 y1, right. I can even put this is x y11, y12, y1n, this can be y21, 22, 2n. For each element here, for each yi, where I varies from 1 to n here, we have the total variation. I can put it here. This is total variation. So, total variation is SSY, between category variation is SS between, and within category variation is SS within. So, we have this category means here, and this is the total sample mean y bar. So, let us see how to conduct this ANOVA analysis using this table. So, to conduct ANOVA, we need to see the eta square. Eta square is SSX by SSY, that is between variation over total variation, which varies from 0 to 1. This can also be put as SSX can be put as SSY minus SS error over SSY. We can say this 1 minus SS error by SSY. So, if you see this, we have term SS error here. So, eta square and is one more statistic known as omega square are more focused on the group information. It tells us about the within group variation, and there is a statistic known as R square, which is nothing but square of the correlation coefficient that tells us about the whole model. So, R square and eta square are measuring two different things. R square measures the contribution of the entire model, the whole model, in explaining the study variation. Eta square and omega square measure the contribution of individual model terms. So, they are different. Eta square has a positive bias, so it overestimates the individual contributions. So, from a practical standpoint, the bias is small. So, it depends upon your situation, or the data behavior, how we have obtained that. So, R square can be significantly inflated by adding non-significant terms in the model. So, there is a term known as R square adjusted. R square adjusted is for compensating the non-significant terms which have inflated. So, we have inflation here in R square, it is inflated, okay, for a complex model. And R square adjusted compensates with the compensate for non-significant terms. So, the R square value has a bias, it overfits the model, there are chance correlations here, the trends in parallel, and certain variable forms can also influence this one. So, R square adjusted is calculated as, I will put it here, R square adjusted is 1 minus this ratio 1 minus R square into n minus 1 n minus p minus 1, where R square is the sample R square, p is the number of predictors, and n is the sample size. A sample size, I mean the total sample size. So, this is R square adjusted, that gives the more close or more accurate information about the fit of the model. So, by fit of the model, I mean if R square value is, let me say, if this is 95%, but it is overfitting the model, it is telling that the model is 95% close to the original data. For instance, I have the data points here, and this is the model here. This is a kind of a cubical model, the way I have drawn it. So, we have various kinds of models. This would be a linear model, this would be a quadratic model, and this would be a cubical or some polynomial model. Okay. Linear, quadratic, and polynomial, that is more than second degree polynomial. So, in this case, if R square value is telling 95% value, R square adjusted value is telling R square adjusted value is somewhat 93%, then this is more close. Or sometimes if R square adjusted value is maybe 85%, then this difference, this 10% difference is overfitting. That means 10% of overfitting. So, this R square is used for the linear model. For the quadratic and polynomial model, we used R square adjusted. Okay, this is for linear model and this is for quadratic or polynomial. So, these terms we need to calculate to see the closeness, to see the fit of our model, and whatever the model we have generated, the ANOVA model would generate the regression models here, and even we can have certain other advanced models for which we conduct the ANOVA beforehand. Advanced models might be neural networks, genetic algorithm, artificial bee colony, though all those techniques are kind of advanced techniques, but ANOVA can give the beforehand and the overall feel that how would our model look like, how would our model behave, what is the curve fitting in case of regression fitting we are talking about. So, this is what ANOVA would help us. So, in one way analysis of variance, the interest lies in testing hypothesis that category means are all equal in the population, as I mentioned before. That means all category means are equal, that means they all come from the same population. So, under this null hypothesis, SS between and SS error come from the same source of variation. In other words, the estimate of population variance of y, this SY square can be calculated as SSX by the degrees of freedom. So, this C minus 1 is the degrees of freedom. This is also my degrees of freedom. So, if you see this estimate of population variance, this is nothing but mean square due to x, which we denote as MSX, and the second one is mean square due to error, in which we have this error degrees of freedom and if we have the category or group degrees of freedom. So, this is MS error. Then we can have the F statistic value here. The F, which I just said, is MSX by MS error. This is equal to SSX by its degree of freedom and SS error by its degrees of freedom. So, this statistic follow F distribution. F distribution, we write it like this: F degrees of freedom 1 and degrees of freedom 2. Please make a note, this D1 is always numerator and this is denominator. So, in this case our degrees of freedom would be F C minus 1 and N minus C. So, F distribution is a right skewed distribution. It is like this, something like this, or maybe like this, or maybe even like this. It depends upon the degrees of freedom for which we are trying to represent this F distribution. Here we can have the alpha value, that is if F value, if F statistic value is greater than this specific value, let me say this value is M. If F is greater than M, we reject H naught, and if it lies in this region, this is accepted. Or in other words, you can say if the probability is P, alpha is my significance level, alpha if I say if it is 0.05 for 95% confidence level or 5% significance level. If P value is less than 0.05, we reject H naught of the equal variances. So F test is the catch of all term for any test that uses F distribution. In most cases when people talk about F test, they may are actually talking about the F test to compare two variances. So F test, this is used to compare two variances. And please note here that F, let me say 2, 5 is different. This is numerator, this is denominator. This is not equal to F 5, 2. So degrees of freedom from numerator comes first, for denominators comes second. And why are these lines, these three lines 1, 2, 3, why are these different? These depend upon the kind of the degrees of freedom for the numerator and the denominator. Like this line can be for D1 is equal to 1, D2 is equal to 1. The second line, this which is having a lesser slope, this can be for D1 is equal to 2 and D2 is equal to 1. The third line, that is kind of a right screwed normal distribution, this third line is for D1 is equal to 5 and D2 is equal to 2. So for higher degrees of freedom, we can even see the normal trend here. For let me say it would behave like this. If I say D1 is equal to 100 and D2 is equal to 100. So very high degrees of freedom, F is an approximation of normal. So if this null hypothesis of equal category means is not rejected, then independent variables does not have significant effect on dependent variable. This is rejected here, that means the independent variable may have effect on the dependent variable. So in this case the null hypothesis is rejected, that means the effect of a dependent variable is significant. I can say here significant effect. It has significant effect on the dependent variable. The comparison of category mean values will indicate the nature of effect of independent variable. So let us try to compare the category means here. So we have this data here, in which we have the store sales, the in-store promotion and coupon level, and this is store number. So let me recall the steps that we just discussed. First, we will try to identify the dependent and independent variable. Then we will decompose the total variation into between groups and within groups. Then we will measure the effects, that is eta square, omega square, r square. Then we will test the significance for the specific level of significance for the specific significance, let me say 5% significance level. Then we interpret the results. In interpretation of the results, we see that which is the most influential factor here. So, first let us try to identify which is my dependent variable and what are my independent variables. Okay. So, just please make a focused look on this: coupon level, in-store promotion and sales. Which is our dependent variable? What is the store trying to look here? I think you are able to identify this. The dependent variables would be the sales. So, dependent variable is sales. Okay. Independent variable, there are two independent variables. The store number is just the number of store, you can call it a serial number, or this is just the nominal data. Okay, then independent variable is the coupon level and in-store promotion. And in-store promotion. So, if we see this, we can put the types of the scales here, that is it metric or non-metric scales. Dependent variables, yeah, the sales is in a metric scale. I will put the scale here, it is interval scale. And this one coupon level is nothing but these are categories. And in-store promotion is also my categories. You can see 1 and 2, there are two categories here, coupon level. And in-store promotion, there are 1, 2, 3 for coupon 1 and 1, 2, 3 for coupon 2. Coupon 1 and this is for coupon 2. Okay. This is coupon 1 and 2. So, if I say for in-store promotion, this 1 is low, 2 is medium and 3 is high. So, this is my ordinal scale here. So, I will better put it here, this is the ordinal scale. Low, medium and high level of promotion. So, could I divide this into these stores? So, there were total 30 stores, 1, 2, 30 stores. So, I have divided this into 3 groups of in-store promotion, that is low, this is low and medium and number 3, this 3 is high. So, that means we have got 3 categories here, 3 categories, high, medium and low, and the category size is 10. So, this is my group size is 10 and this size, that is number of groups, this is equal to 3, this is equal to 10. So, if I see the degrees of freedom for number of groups, that would be, the df would be 3 minus 1 is equal to 2, and we have sample size is equal to 10, that is group size, n into c, that is 10 into 3 is equal to 30, and degrees of freedom for the sample, if you recall, those were n minus c, that would equal to 30 minus 3 is equal to 27. So, we will use these two terms in the calculations. So, this is the group mean is 8.3, group total is 83, group mean, okay, for high, for medium, for low, we have group means, and we have grand mean of the whole data, of the overall data. This is the overall mean. So, let us see the calculations. SS total, SSY, what was that? That was the variation of each value 10 minus the grand mean. This 9 minus grand mean, 10 minus grand mean, this 8 minus grand mean, 9 minus 10 grand mean, so on. We have 30 items, and we keep on taking the squares of this. This is the sum of squares. So, this is for 10 minus the grand mean, 9 minus grand mean, 10 minus grand mean. So, this is for group 1, group 2 and group 3. We got these values, and we got the final total variation as 185.867. Oh, this is the calculation, this is how the mechanism of ANOVA work. Actually, when you just know this mechanism, when you work on the software, when you work on the packages like R package or Excel, or if you have some SPSS or Minitab softwares, you need not to do all these calculations. This all would be done by the computer, but you should know that what is happening, the GUI, what is the software doing, what is the graphic user interface in that. So, this thing would help you in that, understanding how ANOVA works. So, similarly, we have SS between. SS between is nothing. If you see, this was the between means, the grand mean, and this means 10 minus 6.067. Then this 10 minus 6.067. Oh, this is nothing but the difference in the categories and the grand mean, that is 8.3, this mean minus this mean, then 6.2 minus 6.067, then 3.7 minus 6.067 whole square. We have only 3 categories, and we have total, this is my group sizes 10, 10, 10. So, this value comes down to 106.067. So, we have taken it for all the values, you can see between. So, SS error is again the category mean. Here it is for category 1, that is high level 8.3, category mean, the difference of this mean from the elements 10 minus 8.3, this 9 minus 8.3, 10 minus 8.3 whole square, this 8 minus 8.3 whole square, so on. We then move to second category 8 minus 6.2, this 8 minus 6.2 whole square plus 7 minus 6.2 whole square, and so on. Then we move to category 3 similarly, and we get the SS error. And we got the total value as this much. So, you might have noted that 106.067 plus 79.80 is equal to 185.867. So, that our decomposition of total variation that we saw before holds good here. So, SSY is equal to SSX plus SS error. So that means 185.867 is equal to 106.067 plus 79.80. So the strength effects, that is eta square, that we can calculate by SSX by SSY, this comes down to SSX value is 106.067 and SSY value is 185.867. So this value is 0.571. So in other words, we can say that 57.1% of variation in sales is accounted by in-store promotion here. 57.1% of sales is due to the variable, this categorical variable, in-store promotion. So now let us test the null hypothesis. We have got the statistic here and this is the value. Let us test the null hypothesis using F statistic here. So F statistic is SSX, that is mean square for x, that is SSX minus degrees of, that's SSX over its degrees of freedom, then SS error by its degrees of freedom. So this is, I will put it again, this is MSX and MS error. This value comes down to SSX value is 106.067, SS error value is 79.8. 106.067 by 3 minus 1 and MS error is 79.8 by 30 minus 3. So this value comes down to 17.94. So we can test this F statistic, we can conduct the F test. We have the F test using F distribution with F. What is the degrees of freedom from numerator here? 3 minus 1, 2, and degrees of freedom for denominator is 30 minus 3, 27. For this, we can see the value of F in the table and we will see whether this value 17.94 is greater than the tabulated value here. If it is greater than, we will reject the null hypothesis and we can say that yes, whatever the hypothesis we are saying here, this sale is due to, I can put here better word is accounts for. So let me test the significance. So for 0.05 significance level, we can see the F table here. So this is F distribution. This is for specific alpha value. In this case, alpha is 10%, 0.1 is 10% or 0.1 significance level. So in this case, we have degrees of freedom in the numerator, in the columns, and degrees of freedom in the denominator in the rows. But this table is not for our test which we are conducting, because this is for specific alpha value. The second table, yes, this table is for 0.05, that we have considered the alpha value here. So for this value, let me see for 2 and 27 degrees of freedom. So for 2 degrees of freedom, we will select this column, and for 27 degrees of freedom, we have with 25 and 30. We select these columns for 25 and 30 and we can extrapolate the value for 27 here. So, this value is 39, 3.39 and 3.32. The in between value, if we say that value comes down to F value, it is tabulated, is 3.35. So, we found that the tabulated value, that is F 227 value for 0.05 alpha is equal to 3.35. So, then we see that this value is far less than 17.94. So, if I say this is my let me suppose my F distribution here would be something like this, and this is my alpha, this is alpha is equal to 0.05 and this alpha value here is 3.35 and my F value, the calculated F value is something very far, that is 17.94, that is far from my significance level here. So, this is in the rejection region. Now, we can conclude that we reject null hypothesis. Null hypothesis would be that no effect of in-store promotion. So, this hypothesis is rejected. An alternative hypothesis, that is reject H naught. So, this holds true. That means we can say that the calculated value, because is greater than the critical value or the tabulated value, therefore, the in-store promotion has significant effect on these sales. So, this is the next step. We have tested the null hypothesis. Now, we will move to the final step, that is interpretation of the results. So, this is the significance level testing, that is we rejected the null hypothesis, and the interpretation of results is the same which I just said, the in-store promotion has significant effect on the sales here. So, we have completed the 5 steps: identify the dependent and independent variables, then we decompose the total variation, then we calculated the statistic value, then we test the null hypothesis. After null hypothesis is tested, we see that is the null hypothesis rejected or not. It is rejected, then we have interpretation of results, that is our independent variable has significant effect on our dependent variable. So, this was our analysis of variance, the mechanism here. So, when you will do this in SPSS window or we will do this in R package, we will show the examples over there as well. We call it CRAN R. You will see these kinds of windows. So, what do they say? You just retrieve the data from the Excel or CSV file, then we put the syntax for ANOVA and we get these values between groups, within groups, total variation, the degrees of freedom for these. So, this is actually total degrees of freedom. Total degrees of freedom is nothing but n minus 1. So, it is actually this plus this is 2 plus 27. So, it is C minus 1 plus n minus C. This is for category. So, if I plus this one, degrees of freedom total, this comes down to n minus 1. Then we have mean square values and we have F ratio. So, this was one way ANOVA. Effect of in-store promotion on the store sales is significant because the tabulated or the critical value here was 3.35. So, this 17.94 is greater than 3.35. So, this cell means also it is giving here. So, there are certain assumptions in analysis of variance. These assumptions are bound to be met. If they are not met, then analysis of variance technique does not hold good. So, what are the assumptions? Number 1, the sample follows normal distribution. That is, if I plot all the sample items, it should follow this normal distribution. How do we test this? We actually do the quartile test. We put the standardized normal distribution here and we have standardized sample items, and we see that what is the correlation between them. Do the line is close to this 45-degree line? If it lies like this one, yes, we can say that they are very much following the normal distribution. So, this is known as QQ plot. QQ is nothing but the quantile plot. Please note, I have put quantile here because we can divide it into number of parts here. If we say the quartiles, like in the box plot, we have 3 quartiles, Q1, Q2 and Q3. We have divided the whole data into 4 components here, and the Q2 was the median, if you remember. So, in this case, we quantile plot, we can say the each, let me say if there are 10 different parts here, this is Q1 to Q10 and equal number of data points are here in each slot here, Q2, Q3. So, this sample follows normal distribution. We will see this graphical, this visualization when we will see the assumptions of ANOVA in our package. We will see are these assumptions being met or not. So, next is independence of errors. That says that the errors between the cases are independent of one another. There is no dependence of errors. The errors are totally independent and there is some random chance that errors are coming. So, next assumption is that absence of outliers. Absence of outliers. For instance, if this is my data and this is the total variance plot here, this could be the outlier, these points might be the outlier. So, absence of outlier, because this outlier would affect my data. If, for example, if this is my model, this is the data and this is the model here. So, if I have a few outliers here, 1 or 2 points which are far behind, the model would come like this. Like these outliers would affect my model. It will try to attract the model, the line toward itself, these outliers. So, that would affect. Now, this point I was mentioning here, this is the variance here. So, it states that the variance has to be homogeneous. Number 4 is homogeneity of the variance. That is, population variance in different levels of each independent variable are equal. So, they are equally distributed here. So, next comes the n-way analysis of variance. N-way analysis of variance is nothing but we have more than one factor. like we had only one factor, that is in-store promotion in the previous example. In n-way analysis of variance, it is often concerned with the effect of more than one factor simultaneously. For example, the advertising levels and price levels, both, how does it depend upon the brand sales? For example, they are we divide the advertisement, the level of advertisement into three categories: high, medium, low. They divide the price of the product into three categories: one, high, medium and low. There are two categories here, that is the two factors we can say. And what is the effect of these two factors on the sales? In this case, two-way analysis of variance would happen. Another example I can take here, I can extend the example which I took before, the familiarity with the NPTEL courses, NPTEL portal, and the number of students who register. If I say this was the one factor, familiarity, high, medium, low was one factor. The number of courses taken, the number of students in the courses is my dependent variable here. If I take another factor, that familiarity with the NPTEL courses, second factor if I take reputation of the specific institution, specific IITs, IIT Kanpur, IIT Madras, IIT Kharagpur, IIT Delhi. These are the two factors, reputation, high and low, depending on the quality of the courses which are delivered by the specific institutions. So we have the quality of the courses depending on the institution and the familiarity with the NPTEL portal. The NPTEL courses are there. These two factors if are there, then again we have two-way ANOVA. So I will try to continue my previous example here and would calculate the SS total as SS due to x1 and SS due to x2 and SS due to x1 and x2 combined. This is known as interaction effect. These are known as main effects. So we had two factors here, coupon level and in-store promotion. We did first in-store promotion and sales. Now we will do the in-store promotion and coupon level on sales. They have coupon level 1 and coupon level 2, the two levels of category here. We have three levels of category here in in-store promotion. How does this affect our sale? We will see this. So not to forget here, this is actually the perfect model. If we do not have the error here, we need to put SS error, that is SS within category. So in this case we have the overall effect that is known as multiple eta square, and we have omega square as well here, that is the individual effects here. So this eta square for if I say two-way ANOVA x1 and x2 here, this eta square is calculated as SS x1 plus SS x2 plus SS x1 x2 by SS total or SSY. And in this case F statistic would be SS x1 plus SS x2 plus SS x1 x2 by the degrees of freedom for n, this is F statistic here, over this is mean square for x1 x2 and x1 x2 combined, this over the SS error by the degrees of freedom for error. So this is nothing but mean square for x1 comma x2 comma x1 x2 by mean square for error. So degrees of freedom for numerator here would be the degrees of freedom for category 1 plus degrees of freedom for category 2 plus combined degrees of freedom for category 1 and category 2. category 1, category 2, combined category 1 and category 2. That comes down to C1, C2 minus 1. And degrees of freedom for denominator for this F test would be degrees of freedom for total all the values minus C1, C2. Okay. So we can calculate this F statistic to see the overall effect. We can even see the F value for the individual effects. For example, for interaction effect F1, X1, X2, that would be S for X1, X2 by degrees of freedom for the numerator here by SS error by degrees of freedom for denominator. So this is MS X1, X2 by MS error. So for this was for the interaction effect. For the main effect, let me say for X1, this would be again SX1 by degrees of freedom for the specific X1 and SS error by degrees of freedom for the denominator. In this case, the degrees of freedom for X1, X2 is degrees of freedom for numerator here is C1 minus 1 into C2 minus 1, and degrees of freedom for denominator here is N minus C1, C2. And in this case, degrees of freedom for numerator would be for this category 1 C1 minus 1, and degrees of freedom for denominator here would be N minus, that is error, N minus C1, C2. So if I consider the two categories here, this kind of table, you can do all the calculations if you want. You can do that in Excel or maybe manually you can do, but I'll show you the table, that is an SPSS output here. So we have the promotion, the coupon and combined. This is category 1, this is category 2, and this is actually X1, X2, and this is X1, X2 combined. So we had for promotion, this is the sum of squares, and for coupon level, if we see, this is the sum of square. We had 3 categories. This is 3 minus 1 is equal to 2. We had 2 categories, 2 minus 1 is equal to 1. The total is 2 plus 1, 3, and combined is nothing but sum of this. This is sum of these two, and interaction we have, see this into this, 2 into 1 is equal to this 2, 2 into 1 is equal to 2. So what we can see, we have the F values for 2 factors and the combined F value, and we also have the two-way interaction and the total for the model here. So we can see here that the F value, as the significance of F, the probability of F is less than 0, less than 0.05 here. This one and this one, these two, that is the promotion and coupon level both are significant. The interpretation would be number 1, promotion, that is the in-store promotion, and coupon level significantly affect the sales. This is number 1. Okay. Number 2, we can see that which has more significance, which has more influence on this. In that case, again F is the criteria that would decide. In this case, coupon level is having larger value, but these two values are close, 54 and 55 are close. We can say that coupon level is having higher influence on sales. If I suppose that this for promotion the F value, let me say it would have been something like 14, and for coupon level it would have been 55. So we can test the significance also. Is the difference of these two values significant or not? Then the third interpretation here is 1, 2 and 3. Third interpretation here is that the interaction, this is the interaction, this value is greater than 0.05, therefore no interaction effect. So the third interpretation I will put here, interaction effect is not significant. So these are the interpretations or the results of our ANOVA table. Also we have omega square here. Now what is omega square? Omega square indicates what proportion of variation in the dependent variable is related to a particular independent variable. This is as a proportion. Okay. So this is calculated only for these significant variables here, because this is less than 0.05. So this is calculated. Omega is calculated, omega square is equal to the SS x minus degrees of freedom for x into MS error by SS total plus MS error. So if in this case, if I calculate the value of omega square for promotion and for coupon, the values comes down to 0.557 and 0.280 respectively. So as a guide to interpret this thing, we can say that a large experiment effect produces index of 0.15 or greater, and a medium effect produces an index around 0.06, and a small effect produces an index of 0.01. So this is large, this is medium, and this is small. We are talking about the omega square here. Okay, if it is less than 0.01, it is small. If it is between 0.06 is less than, omega square is less than 0.15. So in the present example here, 0.557 and 0.280 are both greater than 0.15. Therefore, it has large effect. Large, better to put, large experimental effect. So this was analysis of variance for two factors, or we call it two-way analysis of variance. Similarly, we can conduct n-way analysis of variance, and the multiple factors could be identified. We can have the list of factors, but please mind it, the more we add, the more factors we have, more is the value of R square that is inflated. So value of R square would be higher for more number of factors. In that case, R square adjusted value has to be seen to see the fit of the model. And also we have R square predicted, and also we have R square, we have R square predicted, R square adjusted, and the normal R square. So this R square looks good, but there can be serious problems with an overfit of the model. For one thing, the regression coefficients represent the noise that rather than the genuine relationship of the populations, that is the unaccounted factors could affect this one. So this adjusted R square can compensate that. Moreover, the predicted R square value is designed to detect the overfitting as well. So next is analysis of covariance. So let us see this example in which we have these two factors, coupon level and in-store promotion. These were the factors categories, and there is another variable, that is clientele rating. What is the rating of the client? And this is in interval scale. And then as I mentioned earlier, if we have the interval scale as well as categorical scales, the analysis of variance is then called as analysis of covariance. So when examining the mean values of the dependent variable related to the effect of the controlled independent variable, it is often necessary to take into account the influence of the uncontrolled independent variable. For example, in determining how different groups exposed to different commercials evaluate a brand, it may be necessary to control the prior knowledge of the customer, of the groups here. In determining how the price level will affect a household consumption, it may be essential to take the household size into account. For instance, in this case, the clientele rating, if the client is having high rating, the purchasing by this client might be higher, this might affect. So in this case, we will conduct analysis of covariance. So this is the table here, these are the main effects here, this is the covariance, this is actually the interval scale. So these are in my categorical scale, the factors here. So in this case, we have again the F statistic value. So we can do the similar interpretations from this table as well. In this case, the clientele rating is not significant. This value is greater than 0.05. That means the clientele rating does not have or does not influence my sales here. So next, there are certain issues in interpretation. There are interactions, and there are relative importance of the factors. First, I will take the relative importance of factors. The experimental designs are usually balanced in that each cell contains the same number of respondents, as I had 10 stores in each cell here. But sometimes this is not possible. So this kind of design, when each cell is having same number of respondents, that is known as orthogonal design. So it is possible to determine the relative importance of each factor in explaining the variation in dependent variable in this case. So interactions are when the two variables are interacting each other. So for instance, if I plot this here, let me say sales, and the two variables here are my coupon and in-store promotion. This is not interacting with each other. Like if with increasing this, this is also increasing. So there is no interaction. We can have some interaction in certain cases. For instance, if it is like this one, in this case we have the interaction that is ordinal, that it has, this one is greater, this one is smaller. That is, the lines are not exactly parallel here, but we can see that is the interaction significant or not. Although interaction is there, but significance also need to be tested. Then we have disordinal interaction also. This is the interaction, for instance, if it is like this one. See, this is increasing. If I say there are three values x11, x12 and x13, this 1 and I could put A and B. This is increasing at this point and again increasing. The B is increasing and again the slope is higher and it is increasing. A is first decreasing and then increasing. So, there is a difference. So, this is large, this distance is large, this distance is small, again this distance is large. So, there is an interaction. So, these things, for example, if I do machining, so if you know the mechanical people do machining, they cut the material, they change the tool cutting speed, they change the tool feeder. Cutting speed is the, for instance, the rotation of the workpiece which is being cut here. Okay, it is the workpiece is rotating, it is cut by the tool. The feed is the rate of cutting here of this tool. This can have a transient behavior. For instance, a certain at lower speeds, the cutting, let me say I am trying to see the cutting force here or maybe roughness of the workpiece. Any response I can choose here. Speed, feed. Also I have put A as speed and B as feed. So, here I can see the feed is increasing from level x11 to level x12, but the increase from level x12 and x13 is higher, the slope is higher. However, at lower speeds, this is low speed, this is high speed. At lower speed, the force is higher. At intermediate speed, the force is lower, and at high speed, the force is again high. So, this has an interaction. The previous one was ordinal. So, this is disordinal. Disordinal, but non crossover. Sometimes we can have the case when if I say the same case for different machines or for different material or for different tool combination, tool work combination or for different environment, it can behave something like this as well. So, this is again disordinal, but we have crossover. So, this is disordinal and also we have crossover here, it is crossing. So, these transit behaviors can be like this as well. So, for the non-metric analysis of variance, there are certain tests like K median test. This is actually known as K sample median test. So, this is non-metric analysis of variance. This examines the difference in the central tendencies of more than two groups when the dependent variable is measured on an ordinal scale. In this case, y or dependent variable is ordinal. So, it is non-metric. So, in these cases we can have these kinds of tests which are I can say that out of the scope of this course, but we can provide notes to you for this. Also we have multivariate analysis of variance, that is ANOVA. So, what is ANOVA or multivariate analysis of variance? It is similar to ANOVA except that we have more than one dependent variable. So, in ANOVA the null hypothesis is that the vectors of means on multiple dependent variables are equal across groups. Vectors of means are equal across groups. So, multivariate analysis of variance is appropriate when there are two or more dependent variables that are correlated. So, next we will meet in the R session for analysis of variance. We will take the certain examples here. We will do ANOVA test for 2 factors, for 1 factor, for 2 factors, and for multiple factors, and we will see how to interpret the results. We will see how the assumptions are being met and what to do if assumptions are not being met here. Thank you.